My guest today is Andy May.
Okay, this talk is an abbreviated version of the contents of two reports on the bias and distortions presented by the Intergovernmental Panel on Climate Change, or IPCC, in their latest major report called AR6. The first report was written and published by a Clintel group of scientists. The title is The Frozen Climate Views of the IPCC, an Analysis of AR6. The second is a series of 7 posts I published on my website this year entitled Climate Model Bias. A search for Andy May Climate Model Bias and you should find them. The full 3-volume AR6 report contains 7,519 pages, and while my recent series Climate Model Bias addresses all 3 volumes, this talk will only summarize the discussion of Volume 1, the physical science basis, and the climate models it describes. What does AR6 say? The top quote is the over-the-top summary of the report provided by the United Nations Climate Change Office, called the UNFCCC Secretariat. This summary is not an unbiased look at either AR6 or the science. The mission of the IPCC is to provide an open, transparent, and objective assessment of climate science that reflects a diverse range of views and expertise. We will see how well they did. First, let's review the conclusions of the previous reports. FAR, the first report published in 1990, reported that the warming over the previous 100 years was consistent with the results from their climate models, but also consistent with expected natural variability. This report was very balanced between the idea that humans are causing climate change and the idea that most of the warming is due to nature. SAR, the second report, published in 1995, agreed with the FAR conclusion in its first draft issued in July of 1995, but by the time the final draft was approved in November, the conclusion had been changed to say that a human influence on climate could be discerned. This change, made by politicians to what the scientists had written only months earlier, was widely criticized in the press at the time. Even Frederick Seitz, who served as president of the National Academy of Sciences and the American Physical Society, wrote a 1996 op-ed in the Wall Street Journal calling the change a major deception on global warming. TAR, the third report, was published in 2001. This was the report that introduced the notorious hockey stick. The hockey stick was flawed and caused years of controversy before it was finally debunked by the Wegman report, the National Academy of Sciences, Willie Soon, Steve McIntyre, and Ross McKittrick, but nonetheless was used as evidence to upgrade the SAR conclusion to most of the observed global warming over the last 50 years is likely due to humans. AR4, the fourth report, was published in 2007. It was essentially the same as TAR, but they changed likely to very likely. They did admit in AR4 that the hockey stick was flawed. AR5, the fifth report, was published in 2013. There was no significant change from AR4. AR6 was published in 2021. It made the bold leap from most of the warming is due to humans to all the warming is due to humans. This was despite the fact that the AR6 models had a larger spread of climate sensitivity to CO2 than the AR5 models did. They had to create a special subjective statistical model to estimate the range of climate sensitivity, so the uncertainty appeared to narrow. The apparent narrowing of uncertainty was totally manufactured. AR6 admits that their climate models are worse relative to observations than those used in AR5. This table provides the best estimates of the climate sensitivity to a doubling of CO2, or ECS, for the IPCC reports. And the 1979 U.S. National Academy of Sciences Charney report. All the ranges are based mostly on IPCC CMIP climate model results, except for the AR6 estimate, which is based on a subjective model. Except for AR4 and AR6, the range of likely values is 1.5 to 4.5 degrees C per doubling of CO2. Obviously, the evolution of the conclusions shown in the previous slide had little to do with better modeling. This is admitted in AR6 on page 1008, where they write that no systematic convergence in model estimates of ECS has been seen. And in fact, the overall intermodel spread in ECS results for CMIP6 is larger than for CMIP5. Climate model uncertainty increased from AR5 to AR6, not a good sign. The bottom row of the table shows the result when Nick Lewis redid the subjective AR6 statistical model. He updated the data a bit, but the major change is that his model is objective and not subjective. He computes a range of 1.8 to 2.7 degrees C per doubling of CO2, both lower and narrower than the AR6 estimate. This is similar to Lewis and Curry's 2018 ECS estimate based only on observations since 1870 of 1.2 to 2.7 degrees C. The IPCC model estimated climate sensitivity to CO2 appears to be biased high. This conclusion is supported by work done by Ross McKittrick and John Christie, as well as the conclusions of AR6 on page 444. Thus, they report that they are more certain that human emissions are causing global warming, but they are less confident in how much warming is influenced by human emissions. Something is not quite right. There are three types of scientific models. In this talk, we will discuss the IPCC CMIP mathematical climate models and their conceptual model that additional greenhouse gases are causing all the recent warming. The foundation of their climate models, what they were created for, was to test the conceptual model. So what is a mathematical scientific model? It's a mathematical representation of a chosen reality based on well-established physical and chemical principles. It is built using assumptions and observations that collectively are called the conceptual model. Then the model is used to hindcast, look backward, and forecast, look forward. The hindcasted values are compared to observations, and the errors are examined. The modeler then runs various trials, each with slightly different assumptions and parameters, and finds the model that fits observations best. This is the model he uses to predict the future. Then he waits to see how he did. According to George Box, the famous University of Wisconsin statistician, the modeler should never fall in love with his model because all models are wrong. All models have a lifetime. Eventually, they all die and cannot be saved. They will never be correct, no matter how much you fiddle with them or how elaborate you make them. It is a sure sign that a model is near death when your changes make it worse, as happened in AR6. Models are not data. They are learning tools. The takeaway from any model is what you learned building it. The model itself is of little value. It is uncontroversial that only two things control the surface temperature of the Earth: the amount of energy received from space and the time the energy remains in the climate system. Everyone agrees with this. Where they disagree is on what influences the residence time. The IPCC would have you believe the only control on the energy residence time is the energy exit delay caused by greenhouse gas emissions. Others say, wait a minute, the sun doesn't vary very much in its output, but it does vary some. These variations historically correlate with climate changes. The plot on the right is a beryllium-10 ice core proxy of total solar irradiation, or TSI, from 0 AD to the present. It correlates with known historical climate changes as identified across the top of the graph. Recent solar grand minima are also identified below. It emphasizes that the sun and climate are variable at all times. Colder periods are coincident with solar lows. Further, many decadal and multi-decadal ocean and atmospheric oscillations, like the Atlantic multi-decadal oscillation, the North Atlantic oscillation, and the Pacific decadal oscillation, have been discovered since the modern CO2 hypothesis was introduced in 1979. These surely have an influence on the residence time. It cannot all be greenhouse gases. The Earth is not a static thermodynamic body. Its surface changes all the time with the weather. Radiation efficacy, or the temperature change due to a change in the amount of radiation received, is different for different sources and locations. The most obvious difference is between greenhouse gas radiation and solar radiation striking the ocean surface. Oceans cover 70% of the Earth, and they absorb most of the solar and greenhouse gas radiation as a result. Solar radiation has a shorter wavelength and can penetrate over 100 meters into the ocean. Greenhouse gas radiation cannot penetrate the ocean surface beyond a millimeter. This results in a very short energy residence time in the ocean for greenhouse gas radiation and a longer lifetime for solar energy. Thus, solar energy output changes have a greater efficacy. Bob Irvine has computed that solar energy has over 3 times the efficacy of greenhouse gas radiation. This was not considered by the IPCC, who believe that solar efficacy is less than greenhouse gas efficacy based on climate model results. Energy absorbed deep into the ocean stays there quite a while. It raises the ocean temperature and increases the ocean heat content, and only slowly makes its way to the atmosphere, which can eventually radiate it to outer space. Infrared greenhouse gas radiation only stays in the ocean for a very short time. It is carried away via evaporation or by the wind very quickly. Warren White has shown that changes in ocean heat content are almost an order of magnitude more than can be accounted for by changes in the radiation from the sun over the course of the Schwabe 11-year solar cycle. Changes in ocean temperature are much more than expected. These differences are due to the extra energy residence time of sunlight over greenhouse gas radiation within the ocean. It seems likely the IPCC has it backwards due to their reliance on models, which just spit out what was programmed into them. This is an apparent error that should be investigated. This graph compares various solar activity reconstructions from sunspot observations. Sunspots are considered a good proxy for solar output, with high sunspot counts equating to higher solar radiation output. Grand solar minima, such as the identified Maunder minimum and the Dalton minimum, are readily recognized since the amplitude of the Schwabe 11-year solar cycle is very reduced in these times. Grand solar maxima, such as the modern solar maximum from about 1930 to around 2010, are harder to see. These are periods when the smoothed sunspot number remains above 50 for 2 solar cycles or longer. The modern solar maximum lasted about 80 years and was centered in 1970, according to Ilya Usoskin. This is the longest solar maximum since 1200 BC, 3,200 years ago, according to solar proxies. Solar maxima do not have an instantaneous effect since the change in solar output is small and they work by accumulating excess thermal energy in the climate system, especially in the oceans. Very little energy escapes directly to space from the oceans. It must first be transferred to the atmosphere and carried to a location and altitude where it can escape to space. Here we compare the same sunspot records to the Hadkrut-4 surface temperature anomaly. We notice the late 19th century temperature decline as solar activity decreases to a minimum around 1910. Then they rise rapidly until the 1940s and fall until about 1976, as solar activity drops a bit during the 1960s and early 1970s. Then temperatures began to rise again in the 1980s and 1990s, only to stall in the 2000s prior to the 2016 Super El Nino. The modern solar maximum is now over, so some reduced rate of warming or even cooling in the next few decades is to be expected if solar variations make a difference. This is a graphic showing the IPCC modeled components of global warming since 1750, just after the end of the worst part of the Little Ice Age. Their models say that the sun's variability had essentially no impact on global warming, or perhaps a very small negative impact. They claim volcanoes have a slightly larger negative impact on global warming, so all the warming is due to human activities in their model. This might be correct, but who knows? The alternative idea that nature caused some of the warming is still entirely possible and should be investigated, not ignored. The emphasis the IPCC places on global average surface temperature and the use of the phrase global warming suggests that atmospheric and oceanic circulation of thermal energy are not important in discussions of climate change. The IPCC makes much of the fact that the only way Earth gains thermal energy is through radiation absorbed by the atmosphere or the surface from outer space, and the only way it loses energy is when radiation is emitted to outer space. This is true, but the apparent corollary that movement of thermal energy from one place to another on Earth's surface makes no difference in the overall energy imbalance is not true. Convection largely controls the residence time of the energy within the climate system. When the average residence time is short, Earth cools. When the residence time is long, Earth warms. Critical air circulation patterns control convection. To demonstrate this, we need to examine 6 critical areas of climate and geological research. The first is the areal distribution of incoming and outgoing radiation around the globe and the distribution of net radiation flux, that is, incoming minus outgoing radiation. Next, we will examine energy transport from the tropics, where there is a surplus of thermal energy, to the polar regions, which have a deficit or a net loss of thermal energy to space. This thermal energy transport is called meridional transport of energy. When meridional transport is strong, Earth cools. When it is weak, Earth warms. The lower figure in this slide illustrates strong meridional flow in orange and weak or zonal flow in red. The orange pattern cools the globe and the red pattern warms it. The red pattern delays meridional transport to the polar regions. Thirdly, tropical temperatures do not vary much over geological time because over the oceans they are limited to less than 30 degrees C by evaporation. So-called global warming happens almost exclusively in the higher latitudes, not in the tropics. The upper figure in the slide shows the total energy transport in black. North is positive and south is negative. The ocean transport is in blue, the dry air transport in red, and the latent heat transport by evaporated water in green. As you can see, most transport is via the atmosphere. The fourth critical area we need to examine is how the difference between the equator and the poles forms a characteristic equator to pole temperature gradient. Various temperature gradients and their associated global average temperatures, labeled GAT in the slide, from Earth's past are compared to the current gradient in the left-hand graph, our current average temperature is between 14 and 15 degrees. It is below average for the Earth. The current temperature by latitude is shown as plus signs, the dots. The fifth critical point is that the equator to pole temperature gradient today is relatively steep, suggesting the climate of today is unusually cold. The final point is that the temperature gradient powers meridional transport. The last column of numbers in the slide is the percentage of the Phanerozoic, the past 500 million years, that the Earth has had each gradient in the graph. 59% of the time, the Earth has had gradients representing from 19 to 20 degrees C, global average temperature, or 4 to 5 degrees warmer than today. The left-hand graph is based on a model created by making 100 maps of ancient Köppen climate belts around the world. Each map represents the estimated paleoclimate of a 5 million year period, so the maps cover 500 million years. Temperatures cannot exceed 30 degrees C over the oceans or any significant body of water, and since most of Earth's surface is water, this greatly limits the global average temperature, regardless of the greenhouse gas concentration in the atmosphere. While the temperature gradient powers meridional transport has many modulators, and the gradient is only one of them. It is unclear exactly how the temperature gradient and meridional transport interact, but clearly they are the main drivers of global climate change at all timescales. The current climate is unusual in Earth's history. It is unusually cold, not unusually hot. Scotise's work is very well accepted in the geological community, yet it is ignored by the IPCC, who prefer to proclaim current warming is unprecedented. In fact, although Chris Scotise is famous for his work on paleoclimate, a search for his name in AR6 WG1 comes up with nothing. In fact, his name is not referenced in any of the AR6 volumes, although his findings are relevant to all three. The right-hand graph compares the IPCC range of projected global warming as a red or pink band to Scotise's reconstruction of global average temperature for the past 500 million years. When global temperature is below 18 degrees C, as it is today, ice caps can exist at the poles. When temperatures are above 18 degrees C, ice caps are unlikely. The boundary at 18 degrees C is shown as the black line in the middle. Basically, if the IPCC projections are correct, we will just return to the normal surface temperature for the planet. The current rate of global sea level rise is below the accuracy of our current ability to measure it, as discussed in Kip Hansen's Chapter 5 in Kroc and May. The graph shows three respected estimated rates. The sea levels are shown as reported, and they have different 0 points. The Gevrejeva et al. Estimate in blue is 2 millimeters per year, plus or minus 0.3. The one below that is the Church and White estimate of 1.7 plus or minus 0.3 millimeters per year. These estimates are both from tide gauges, although the Gevrejeva estimate does try and include the satellite data from 1993 to 2009. Due to the overlap of the author's estimates of uncertainty, the two estimates are statistically equivalent. The lower estimate, shown in gray, uses all the NASA satellite data since 1993. It shows a rate of 3.3 millimeters per year. The satellite record is too short to be meaningful. We need at least 60 more years of data before we can derive a meaningful rate from satellites. The satellite data only covers the upward part of a 60-year cycle or oscillation that began in 1991. Global mean sea level has been rising for the past 170 years. but the rate is cyclical. The cycle shows up prominently in the graph from about 1930 to 1991 in the Gevrojeva et al. Reconstruction. It is also seen, albeit in a more subdued fashion, in the Church and White reconstruction. Thus, any estimate of the rate of rise based on a reconstruction, satellite or tide gauge or combined, that is shorter than 90 to 120 years is erroneous. Sea level fell during the Little Ice Age until about 1861, when it began to rise. All the rates since 1900 are projected to 2100 in the upper left box and show sea level rises between 5 and 10 inches by 2100. These increases are much less than the average daily tidal range of over 1 meter. Since a small rise in 76 years is unlikely to be noticed, it should be noted that here that sea level is not the same in all oceans as one might expect. In Panama, sea level is 20 centimeters or 8 inches higher on the Pacific side of the country than on the Atlantic side. This is about the global sea level rise expected between now and 2100. Even more important, the tidal range on the Pacific side is much larger than on the Caribbean side. Measuring global mean sea level is made extraordinarily difficult by the changes in mean sea level from ocean to ocean and the related changes in the daily tidal range. Gevrojeva points out that tide gauges are confined to continental and island margins, and most of them are in the northern hemisphere. The tide gauge records don't all cover the same time period, and they are attached to land that sometimes rises and falls itself. Gevrojeva points out that it is not easy to combine the various records into a single global sea level curve. In a like fashion, any estimate of acceleration and the rate with any of this data or any combination of it is little more than a guess. Polynomial fits to all these series can show some acceleration, but the fit to the polynomials is statistically no different than a linear fit to the same data. The IPCC and Al Gore like to tell us that higher temperatures will lead to stormier weather. Research by many climate scientists, including Zhongwei Yan, Phil Jones, Anders Moberg, Susanna Costas, Felipe Sorel, and many others, dispute this idea. As the planet warms, the equator to pole temperature gradient decreases since tropical temperatures barely change. A smaller equator to pole temperature gradient provides less power for storms. Earth's atmosphere is like a heat engine. It is powered from below, and as the heat moves through the atmosphere, it does work, just as steam moving through a locomotive does work on its way to the smokestack. The work it does is our weather. When the gradient is steep, as it is today, it does more work, and the world is stormier. Leon Berry tells us that most heat is moved from the tropics to the poles by mid-latitude storms. If there is less heat to move, there are fewer and less severe storms. Zhongwei Yan tells us that extreme weather has decreased, especially in the winter months, since the 19th century. Work by Roger Pielke Jr. and Bjorn Lomborg confirm this trend. On longer timescales, we see that storminess has greatly decreased since the Little Ice Age, which is labeled LIA in the figure on the slide. We have seen that the weakest assumption made by the IPCC is that the sun has remained nearly constant cumulatively since 1750. Tropical temperatures hardly change with time, so global warming occurs in the higher latitudes, which means global warming lowers the equator to pole temperature gradient, which means fewer and less severe storms, both tropical and mid-latitude. There are three processes that work together to keep Earth's climate stable. They are the greenhouse gas effect, meridional transport, and clouds. These processes determine the residence time of absorbed solar energy. The IPCC only focuses on the greenhouse effect and ignores the other two. The bias in AR6 is mostly due to their selection of papers and data. They only choose data and studies that support their idea that CO2 is the control knob for climate change. To make matters worse, they ignore clear warning signs that their models consistently run too hot. The fact that they do run hot, despite 6 major reports, strongly suggests that their models have serious design flaws and may be outdated. They admit, quote, "We assess with medium confidence that CMIP5 and CMIP6 models continue to overestimate observed warming in their upper tropical troposphere over the 1979 to 2014 period by at least 0.1 degrees C per decade. That is 1 degree per century, which is what we've observed. In part because of an overestimate of the tropical SST trend pattern over this period. A critical physical law is that mass and energy must be conserved. It turns out that nearly all the latest climate models, the CMIP6 models, violate this law because their mass and energy budgets do not close at the end of model runs, according to a paper by Irving et al. In the Journal of Climate. The models are also prone to drift, which is an unforced trend in their results, usually to a warmer state. But cooling drift has been observed in some model runs as well. This drift contaminates the forced, that is, changing CO2 or volcanism trends. In some models, the drift is a significant proportion of the warming computed. It results from the parameterization of quantities that cannot be modeled, like cloud cover, and from an imbalance between the prescribed initial model state from observations and the physics programmed into the model. Another culprit can be the coupling shock, when the various model components like the ocean and atmospheric components are merged. This is called boundary shock. Suffice it to say, the fact that mass and energy are not conserved in these models and they drift is a real and significant problem. The model drift is simply the model trying to reach a stable state after the startup or spin-up shocks occur. Equilibrium after spin-up is not reached for over 1,000 years, so letting the model run that long just to get rid of the drift is not practical. Usually when the models are corrected for drift, their mass and energy conservation problems are reduced. It is clear the CMIP models are on the wrong path and should be dumped so they can start over. More Band-Aids, duct tape, and baling wire will not fix these turkeys. George Box addressed this tendency towards increasing model complexity and noted, just as the ability to devise simple but evocative models is the signature of the great scientist, so over-elaboration and over-parameterization is often the mark of mediocrity. This talk is just a brief summary of the contents of 2 important publications. On the left is the cover of the recent Clintel report. The title is The Frozen Climate Views of the IPCC, an Analysis of AR6. On the right is a useful phrase to search for my blog posts on this subject. I encourage you to check out both. They have much more detail on everything discussed here today, as well as a full bibliography. So that's it, Tom. Thanks.
I do have several questions here. One of them is, what do you think is the appropriate value estimate for ECS, for doubling CO2? What do you think, how much warming should we see, leaving everything else the same?
Okay, well, obviously I've spent an awful lot of time looking at that. I don't know what the number is. It's based on data, observations, and real calculations using real data. It almost has to be less than 2. Okay. However, Judy Curry and Nick Lewis's estimate is a maximum estimate, because although they tried to take the Atlantic multi-decadal oscillation into account in their calculation, they assumed everything else was CO2. So their estimate is a maximum. Some earlier estimates are less than 1. I really like John Christie and a colleague of his estimate of about 0.7. I think, to me, most of the evidence says that overall feedbacks are negative. Feedbacks will try and reduce the warming overall net. So it's actually Christie and McNitter. I forgot his name for a second, but they got about 0.7, and I kind of lean in that direction. I think it's less than 1, but it's certainly less than 2.
Note that after the podcast, Andy emailed me to let me know that he had misremembered the climate sensitivity of Christie and McNitter. It was closer to 1.1 degrees C with some caveats. I put a note in the show description.
Did that just confuse you?
No, that's good. Do you think there's a school of thought among the mainstream IPCC folks that they can just look at warming since 1979 and try to extend that forever, as if climate is not cycling up and down, and if you start at a low point, you probably can't just extend that forever?
That seems to be what they're doing. I mean, that's what I observe them doing. The 1970s were very cool, and we're on the upswing of a natural 60 to 70 year cycle, or perhaps we're at the peak and about to go down. I don't really know. I do expect cooling to begin in the next 20 years, but I don't know exactly when in that period it'll start, and or at least a slowing down. It depends on how much of the warming is CO2 and how much of it is natural, and I don't really know that.
Right now, I'm looking at Roy Spencer's graph of satellite temperatures, UAH, and there's this big spike here this year. How much of that do you think may have been caused by the Hunga Tonga eruption, putting water vapor way up in the stratosphere?
I think quite a lot of it. As Richard Lindzen pointed out, I just saw this. He pointed it out 30 years ago. The higher you get in the atmosphere, the more effect water vapor has. So I think when you put that much water in the stratosphere, which is very high, above 30,000 feet, it's going to have quite an effect on surface warming. How long that lasts, I don't know, 2 or 3 years, 4 years maybe. It's the eruption was in 2022, I think, at the beginning, right?
I think so.
Yeah.
Let's see. Another interesting thing from one of your graphs is you showed the Dalton minimum and the year without a summer. Do you think there's some connection between the Dalton minimum and volcanic activity at all, or those are separate?
I think some of that cooling is due to volcanism. I forgot which volcano it was, but there was Krakatoa, maybe. There was a big volcanic eruption around then that I think added to the cooling, but some of it was the solar minimum.
Do you think there's any connection ever between some sort of solar activity and volcanoes on Earth? Somehow there's a slight change in how the sun's pulling on the Earth, anything like that?
I don't see that, but I know it's been proposed by some people. Gravity is going to have some effect on magma, which might have some effect on volcanism. I just don't understand how that works or would work.
Another question is, have you looked at some of this work by Michael Connolly analyzing data saying that maybe the Hadley cell circulation, maybe it doesn't work the way we think it does?
It doesn't work in the way that it's drawn in cartoons. Okay. I've looked at Michael Connolly's work with him, actually, and I don't think he has enough stations to really establish global circulation. The the geography of the Earth, where the deserts are and where the tropics and mid-latitudes begin, suggests that there is some circulation component that you could call the Hadley cell. But the atmospheric circulation is not just straight south to north in the northern hemisphere and north to south in the southern hemisphere. It's more complicated than that. It goes in a much more complicated pattern. There's a big east-west component, and there's a lot of change in the winds with altitude. So I think the Hadley cell is a concept that's useful in figuring out climate, but it's not, it's probably not a physical thing, at least not the way it's drawn in cartoons. It's just a component, a vector component of a much more complicated circulation.
So if you had to bet, would you say that it's likely that in the next 100 years, we might see some sort of a cooling scare like we did 1940s to 1970s?
Well, look, never underestimate the media and exaggerating things. So, yeah, if cooling does start in the next 20 years, I'm sure that they'll make a big deal out of it, and I'm positive that they'll blame humans somehow for it.
Based on what you know, do you have any idea of what might happen with the IPCC over the next 30 years? Are they just going to keep pumping these out and say we're more and more sure every time? Or what do you think they're going to do?
Well, man, they've already gotten up to 100%. I don't know how they go higher than that. But certainly somebody at some point has got to realize that after they've been through 6 major iterations with thousands of scientists and billions of dollars, and they've made no progress in calculating the effect of humans on climate, they're going to have to pull the plug on the money. And when they do pull the plug on the money, I'm sure all those scientists are going to find something else to do and something else to frighten us with. But at this point, it's just comical. I mean, 6 major iterations, they're coming to the same conclusion. They're inventing subjective statistical models. It's reached the point of absurdity. After 30 years, you should be able to somehow calculate the impact of CO2 on climate. I think they locked themselves into CO2 is most of it or all of it, and they can't go backwards, even though the data and the technology is all saying that the effect of CO2 is much smaller today than they say.
Do you have high confidence that the modern solar maximum really is over, or do we not know enough and it might surprise us and fire back up again?
Well, let's see. Given the definition of a solar maximum, I think when we get to another solar maximum, it would be a new one using Ilya Yasoskin's definition. And his definition is pretty standard. I think everybody accepts that, everybody I know. So, yeah, I think the modern solar maximum is probably over. I don't see how it could really fire back up again. Yeah.
All right. Any other points you'd like to make before we finish this one off?
No, I'm very, very grateful to the Different City Petroleum Club for inviting me to give this talk and write it. And then this is another opportunity to present it. I hope it makes an impact.
Very good. Yeah, this is great stuff packed with data. So I appreciate your work, Andy May. We'll talk to you next time.
Okay, goodbye.
Goodbye.